Capacity Analysis and Balancing, Part B, the Multiple Part Model Cell. Now that you have mastered the capacity analysis and balancing the one-part model cell, you are ready to learn how to use similar tools for the multiple part model cell. In this tutorial, you will review the PQ analysis process and apply it to the multiple part model cell. Use the lean cell analysis worksheet to calculate an average weighted time. Determine tack time using the average weighted time. Build a tack time average weighted cycle time chart. Calculate time target for each model. Calculate ideal manpower, and calculate your time targets for each product and balance each model in your cell. In this tutorial, we will examine what it takes to staff and balance the cell that makes the interceptor family of parts. There are 8 models of interceptors with varying annual demands as shown in the table below. The GI-104 and the GI-107 have identical processing, so we will group them as one equivalent model. Therefore, we will develop a cell to process 8 unique models with the listed customer demands for each. PQ analysis. Let's start by understanding how each of the parts contributes to the total volume of the cell by doing our PQ analysis. As you remember from our tutorial on the PQ analysis, we do this by sorting the parts by their volume demand for a given period of time and graphing the parts on the PQ analysis sheet. For this tutorial, the demand will be annual. However, remember that you may want to do a PQ analysis for shorter periods due to seasonal demand fluctuations in your product. The PQ analysis tells us the total volume of parts and what percentage of the total each model contributes. This information is necessary for calculating average weighted times in the lean cell analysis worksheet described below. The lean cell analysis worksheet. Next, we will complete the lean cell analysis worksheet. Begin by listing the product model down the left side of the sheet. In the first column, list the annual demand for each model. Next, from our PQ analysis, list the percent of total demand that each model represents. Across the top of the worksheet, list the work elements or components. Then, under each work element, record the raw, the 98% time for each model. Remember, the 98% time comes from the cycle time analysis sheet for each of the models. The cycle time analysis sheet requires 5 observations of each operation and provides us with the average of these observations and a 98% time. Remember, the 98% time includes 3 standard deviations around the menu and accounts for operator and process variation. By definition, this means that 98% of the time we will be able to complete the operation within this time. Next, fill in the average weighted time column for each work element. You calculate the average weighted time by multiplying the percent of total demand for that product by its raw time. For example, the GI-104, GI-107 model average weighted time for the shear operation is determined by multiplying its percent of total demand, 10.67%, by the 15-minute raw time for shearing given us, 1.600 minutes. Continue doing this for the GI-110, GI-115, and so on for each model and each work element. Finally, sum each column to get the average weighted time for each work element. So what is an average weighted time? It is a mathematical construct that represents an average work element time weighted for demand. While no model in the cell has the exact set of numbers as its observed times, the average demand product going through the cell over the course of the year would have these times. We will use each of these times to plot the tack time, average weighted time cycle time chart. To complete the lean analysis worksheet, sum the average weighted time for each work element to determine the total labor and automation for each work element in the average weighted model as shown. Much like we drew the cycle time chart in the Part A tutorial on balancing, then added the tack time to get the cycle time tack time chart, for multiple part models we start with the average weighted cycle time chart and add tack time. Let's draw the average weighted cycle time chart now. Along the horizontal axis, sequentially list each work element name. In our case, shear, punch and break, weld adapter, and so on. The height of the y-axis needs to be tall enough to cover the time it takes to complete the longest work element average weighted time that we calculated. In our case, we calculated the weld sides complete work element to take 55.1 minutes. Starting with the first work element, add a bar for each element until you have plotted the entire process. The bar for each work element should be drawn so that both automated and manual average weighted times are stacked as seen here in clean and dry and paint. Put the color-coded manual time on the bottom and stack the automated portion of the operation on top. This will make balancing steps easier to visualize. Now, calculate the tack time for the multi-model cell. Calculating tack time. The tack time is simply the time available for production divided by the demand for the product. In our case, after calculating the total shift time and subtracting time for breaks and meetings and allowing for 90% capacity, we have 216,000 minutes times 90%, or 194,400 minutes available for work. The total demand for all the models is 5,455 units. So, in this case, the tack time is 194,400 minutes divided by 5,455, or 35.6 minutes. Combining to get the tack time average weighted cycle time chart. Draw a horizontal line across the average weighted cycle time chart at the tack time value of 35.6 minutes and label it. The resulting graph is the average weighted cycle time versus tack time chart and gives you a visual representation of each of your work elements for the average weighted part compared to tack time. Take note of which work elements are above and below the tack time. Work elements below the tack time are easily completed without constraining the cell. However, those above the tack time represent constraints to meeting customer demands and need to be addressed. While each model that goes through the cell may not have the same constraints, it is important to note which work element will constrain the cell's total production and make sure you address that constraint. Manpower. To find the ideal number of operators required for the work in the cell, add all the manual times to complete the process and divide it by the tack time as shown in line D. This number is equal to the ideal number of operators required in the cell. If this calculation results in fractions of operators, you can either work on waste reduction or process improvements until you can get the next lowest full number of operators. Alternatively, you can round up and have a partial resource available to float in the cell and help other operators or resupply consumables to the cell. In our case, we have a total manual time of 131.6 minutes and a tack time of 35.6 minutes. Dividing, we get 3.7 operators required. Since 7/10 of an operator is closer to 1 than 0, we would round up and require 4 operators in this one model cell. In this case, we have chosen to round up and may address areas for additional productivity in the future. Calculating time targets. A product time target is the time it takes to produce that product given the available manpower. Each product will have its own time target. The product's time target is based on 2 factors: the total manual time to make the unique product and the manpower determined for all products, in our case, 4 operators. Products that have high total manual time will have a high time target. Products that have a low manual time will have a low time target. To calculate the time target, divide the unique product's total manual time by the manpower that was determined for all products. If you recall from our initial table of injectors and their demand, we have 8 models being produced with the following demands. Use the times from the Lean Cell Analysis worksheet for each model. Total to the right, the raw manual times to get total manual time required for that product. As an example, for the GI-104, GI-107, the total manual time is 103 minutes. Similarly, for the other products, sum the manual times and put them here. By dividing the total manual time for each product by our available operators, 4 in our case, we get the time target for each product. Balancing the work for the GI-104, GI-107. Now we are ready to balance the work for each product in our cell. We will look at 2 models to demonstrate the technique and to convince you that the process works for all part models in the cell. We will start with the GI-104, GI-107 model, the one with the smallest time target, and then follow with the GI-175, the model with the largest time target. Begin by picking a vertical timescale that covers the full range of all the part manual times. In our case, it must be tall enough to cover our 55.1 minute operation, so we chose a scale up to 60 minutes. Across the horizontal axis, place our 4 operators. Starting with operator number 1, begin adding bars for each work component and its raw time. For the GI-104, GI-107, shear takes 15 minutes and punch and break takes 10 minutes. Totaling this operation has 25 minutes of work, very close to our time target of 26 minutes for this part. The second operator starts with operation 30, weld adapter for 10 minutes, and completes the first part of operation 40, weld sides for 16 minutes. This operator brings 2 to the time target of 26 minutes. The third operator finishes the weld sides complete for 24 minutes, then begins the first part of the weld baffle operation for 2 minutes, completing his 26 minutes of work. The fourth operator completes the weld baffle for 2 minutes, does the test for 4 minutes, clean and dry for 5 minutes. While this part is completing its 5 minutes of automated processing in clean and dry, operator 4 takes a piece of whip that has completed the prior cycle of automated cleaning and does the manual paint operation for 5 minutes. While this part is in paint, operator 4 takes a second piece of whip that has completed the prior paint cycle and does 10 minutes of assembly and packaging. In total, operator 4 has 26 minutes of work, our time target exactly. As you can see, each operator in the cell will have a balanced workload, and the GI-104, GI-107 model can be produced with the 4 operators. The manpower that was calculated earlier using our Tack Time average weighted cycle time chart. We've shown we can produce the lowest time target product. Now let's do the same with the highest time target product, the GI-175. Balancing the work for the GI-175. For the GI-175, our time target is 56 minutes. Starting with operator number 1, begin adding bars for each work component in its raw time. For the GI-175, shear takes 40 minutes, and a portion of the punch and break operation for 16 minutes. Totaling, this operator has 56 minutes of work, our time target for this product. The second operator completes the remaining 9 minutes of punch and break, does 10 minutes of weld adapter, and 37 minutes of weld sides. This brings operator 2 to the time target of 56 minutes. The third operator does 53 minutes of weld sides, completing that operation, then does 4 minutes of weld baffle. You will notice that this operator has 57 minutes of work. This is a minute above our time target of 56 minutes. We need to work some waste reduction activity in this operation to eliminate 1 minute from the current process. The fourth operator does 10 minutes of test, 15 minutes of clean and dry. While this part is completing its 5 minutes of automated processing in clean and dry, operator 4 takes a piece of whip that has completed the prior cycle of automated cleaning and does the manual paint operation for 15 minutes. While this part is in automated paint for 30 minutes, operator 4 takes a second piece of whip that has completed the prior paint cycle and does 15 minutes of assembly and packaging. In total, operator 4 has 56 minutes of work, our time target exactly. As you can see, once we find a 1 minute reduction in the process for operator number 3, each operator in the cell will have a balanced workload, and the GI-175 model can be processed with the 4 operators, the manpower that was calculated earlier using our Tack Time average weighted time cycle time chart. Summary. Congratulations! You have now learned how to balance the more advanced multiple part model cell. You have successfully reviewed the PQ analysis and have seen how it is used to determine average weighted times. Learn how to complete the lean cell analysis worksheet to calculate average weighted times. Learn how to calculate a Tack Time using average weighted times. Built a Tack Time average weighted cycle time chart. Determine the ideal manpower for your multiple model cell. Calculated time target for each model in the multiple model cell, and learn how to balance the work for the models in the multiple model cell. In the next tutorial, we will learn how to document standard work for lean cells.